So I'm going to talk about trachydacite magma storage before the 1257 eruption of Mt Samalas, which was actually one of the most explosive and sulfur-rich eruptions in the Holocene. And we also know from the eruptions of Tambora and El Chichon that magmas of intermediate alkaline compositions are actually capable of producing very large, explosive and caldera-forming eruptions. Yet these magmas are still quite understudied, which is why we want to find out more about them. This leads us to our first objective. So we want to find out how do these magmas accumulate before those large eruptions. This is basically testing a model that was proposed for other explosive eruptions that states a rapid destabilization of a very large transcrustal vertically extensive magma system. And we want to see whether this model also applies for our Samalas eruption. The second question we want to look into is how does the storage before the 1257 eruption compared to the modern storage of the system. So you can see in this picture, this cone in the center is the center of the current activity of the system, and it erupts basaltic andesite lavas from a reservoir at around 10 kilometers depth, which we know from modern seismic studies. Okay, how do we find out more about the storage before the 1257 eruption? So we chose an experimental approach using natural trachydacite pumice from the eruption as starting material for our experiments. When we coarsely crush this pumice, that means that we have natural pre-existing mineral cores, and around these cores we have experimental rims precipitating during the course of the experiment. All our experiments are run in cold sealed pressure vessels between 800 and 1000 degrees and up to 200 megapascal. They're all water saturated and buffered with a nickel-nickel oxide buffer, and the run times vary between 2 and 21 days, although most of them are run for 7 days. Okay, how do we find out more about the reservoir conditions? So we basically compared our experimental results with the natural results, looking into 3 different characteristics. So the aim is basically to replicate experimentally what we see in nature. So the 3 characteristics are, first we looked into the textural stability of the mineral assemblage that we see in the natural samples, and then we also looked into the composition of the minerals and the melt composition as well. So in this diagram here, you can see an overview of all the experiments we've done. And if we zoom into one experiment, this is what it looks like under a backscatter detector. So you see, for instance, plagioclase and orthopyroxene show quite nice and strong, stable experimental rims around pre-existing natural cores. So we interpreted these minerals as being stable and present under the given experimental pressure and temperature conditions. On the other hand, amphibole and clinopyroxene show strong breakdown features, which you can see in these rims here. So we identified these as not being present under these conditions. So we denoted them as white boxes in our phase diagrams. Right, if we look at the mineral stability textures for the individual minerals, for instance, plagioclase here, over a course of varying temperatures, we can see that it's quite stable up until 930 degrees, but it breaks down at higher temperatures of 950 degrees, showing resorbed rims here, kind of leaving the plagioclase stability field. We also see strong pressure dependence for amphibole, so amphibole being quite stable at high pressures, but breaking down at and below pressures of 75 megapascal. So with this information, we can construct a phase diagram made of the different mineral stability curves here. We also see at lower temperatures that we have a high abundance of microlights in the matrix glass, and those were not present in the natural samples. So we interpreted this as showing us proximity through the solidus of the system. With all these textural information combined, we can come up with the first estimate of the pressure and temperature conditions of the magma reservoir, given in the blue area here. The second characteristic we looked into was the mineral rim chemistry, here given for plagioclase. So we combined, or we compared the natural plagioclase rims, which we think represented the final crystallization stage before the eruption. We compared those with the experimental rims given in the colorful symbols here. We saw that especially the high temperature experiments matched quite well with the natural rims. And we could narrow down this field even further because we know that the highest abundance of plagioclase that were present in the natural sample had anorthite contents of about 50 mol%. We saw similar trends for the other minerals given here for pyroxene, and we see that especially at 930 degrees, we have a very good match between the experimental rims and the natural rims. Third characteristic we looked into was matrix glass chemistry. So you see again our experimental results in the colorful symbols here. We tried to match these with the natural composition in the gray area here. And we saw that for a lot of elements, we have matching results for the experimental rims for a lot of pressures and temperature conditions. But for instance, for potassium and iron, only a few experiments were able to replicate the natural compositions. So we could narrow this down as well. We also had one experiment at 930 degrees and 100 megapascal, which matched for all elements the natural composition, which was quite remarkable. Okay, all the information combined from the mineral textures as well as the compositions of the minerals and the matrix glass gave us estimates about the magma reservoir conditions. So the first estimate we had was from the mineral textures given in the blue area here. We could narrow this down given by the results from the mineral compositions in the yellow area. We also had pressure and temperature estimates from the matrix glass composition. And if we combine all these characteristics, we kind of come up with likely reservoir conditions of the Samalas reservoir between 875 and 930 degrees and 100 to 150 megapascal, which is equivalent to a depth in the crust of about 4.5 kilometers. And we also had one experiment which matched quite well for all these characteristics, which is at 930 degrees and 100 megapascal. What is interesting about this pressure range is that it's actually quite narrow. And going back to the questions that we posed in the beginning, this means that we can form large explosive eruptions from magma reservoirs that are accumulated within a quite limited depth range or quite shallow, narrow depth range, which means that it doesn't have to be this vertically extensive transcrustal magma system to generate large explosive eruptions. We also see that from our results that if we have, for instance, a change in the depth of the reservoir, the modern reservoir at 10 kilometers depth towards more shallower regions, for instance, the 4.5 kilometers in the crust, this could indicate that the current system evolves towards more trachydacite compositions. Right, thank you very much.